Okay, so hi everyone. What we're going to look at in this short lecture is infinitesimal rotations. And as I mentioned to you in the previous lectures, we have real problems when it comes to three-dimensional rotations and how to deal with them. So if we've got cameras at two different positions and we want to try and determine how did they get from one position to another. They didn't just disappear from one and appear in the other, particularly if the two images were both taken with one camera. They must have followed some path. We'd like to be able to determine that path in an unambiguous manner if we could, but even if we can't do that, we'd at least like to find a smooth path in between those two places so that we could then determine the different positions that we're in. Now, the trouble is that if you try and find any of those individual rotations in between, you run into a bit of a problem. You can't actually tell from your nine values what exactly was the rotation that took place, because multiple different rotations might fit that, and also the 9 values that you get are, if you try and work back to that, if you try and optimize to it, you're unlikely to find one that's actually a rotation. So you've fallen outside of that group of rotations in trying to get there. So the real problem is that the rotation matrices, if we make small changes to them in order to try and move from one to the other, if we want to see each of the different, which is how calculus and so on works, it tries to make small infinitesimal changes in between two things in order to try and figure out the path getting from one place to the other. It just doesn't work, and the reason for that is the fact that the group of rotations that I mentioned to you, well, they're a group under multiplication, but they're not a group under addition. And they need to be a group under addition in order for us to, they need to operate under addition in order for us to be able to use all our linear algebra on them and to use our calculus and so on. So we've a bit of a problem there, first of all. And what we would like to do is we'd like to find some other space in which we could deal with them in a linear manner. If we could do that, then we could solve a lot of these problems, okay? So two rotations multiplied by each other will give you a third rotation, but a rotation added to even another rotation or added to some other amount will not give you a third rotation, and we need to find a way of actually dealing with that. So tonight's lecture is very mathematical, okay? And if some of the stuff in the other ones was pretty bad in terms of maths, you'll see the same sort of thing here. I may gloss over some of it from time to time because, again, what I really want to get through to you here is the intuitions, and from that you can always dig down into the maths if you've got a sense of what's going on, okay? So I'm going to describe to you first what the problem is, and then we're going to look at, then we're going to determine what it is we need to do to solve it. Then as we go through it, I'll keep pointing back to it. Now that's that bit, and that's that bit done. So what we'll end up with in the end is a solution to, or at least as best a solution as we can come up with to this problem. Firstly, there's a mathematical term which is called a manifold. Okay, now many of you are probably familiar with the idea of a manifold in a car, which is to do with the flow of hot gases within the car. That's not what I'm referring to here, but how many of you have come across the mathematical idea of a manifold? Have you ever heard that term? Okay, so I'm not really surprised that Patrick has, because obviously it would come up a lot in that, and Olivia's presumably come across it in some of her work as well. But most of you are saying no. So I'll give you a very brief, and again, remember that I'm not a mathematician, so I'm not going to stick to all the rules they stick to in terms of being very exact. I want to give you an intuition here. So we've got a three-dimensional world around me here. And I've got a sheet of paper here which is in just 2 dimensions. Now, we could always argue and say, well, there's a certain thickness to this. I want you to pretend that this is 0 thickness, okay? So it has no volume, okay? If I hold this tight and straight, what I have is I have a linear manifold, which is a 2-dimensional manifold inside a 3-dimensional space. So I can move it up and down, I can move it to different places, but it doesn't affect it. Now, in terms of a manifold, what that really means is that if I was to write on this sheet of paper, if I was to write something on it here, I can only write in the 2 dimensions of the sheet of paper. I can't write up off the paper at all, okay? So as regards what's on the sheet of paper here, this is in 2 dimensions. It just happens to exist in a 3-dimensional world. It is linear because it's in a straight line here in both directions as I do it. Okay, so that's known as a manifold. Okay, and we can put things on this manifold. So in the same way as my wallet here can exist within inside this 3D world, I can draw something in this 2 dimensions here which exists within that 2-dimensional manifold, which is then maybe within a 3-dimensional world. And of course it's a 4-dimensional world because it's existing here over time and so on. You can make those things. So what happens if we have something like a curve like that? Okay, so we have a curve like this. Now again, if I was to draw on this sheet, I'm still only drawing in 2 dimensions. I can't come off it. But as you can see there, this is not linear. This is now curved. Okay, so I've now got a curved manifold within a 3-dimensional space. So it's a curved 2-dimensional manifold inside a 3D space. Okay. Now this is a bit more problematic to deal with because we can't operate our linear algebra on something like this. Now this is where I need you to kind of make a leap of faith, because when we talk about the surface over which the different rotation matrices move, so if I make small changes to a rotation matrix, how they move over a kind of a curved space. It doesn't look like this one here in my hand, okay, because it happens to be a 3-dimensional space, so a kind of a 3-dimensional curved space, which is much more difficult for us to try and visualize. So maybe just try and think back to the 2D or the 1D case and just accept that in higher dimensions these sort of things happen. Okay. So the problem is that I can't do my standard linear algebra in order to try and determine how something would move from one point to another in this space, okay, because that's just not going to work. So instead what we do is we try to make a mapping from this curved space to a space that is, you know, in some way linear or straight, okay. And if I can make a one-to-one mapping between those, what I can do is I can figure out where my 2 rotations might be in this mapped space, in this linear space, and I can then find a path along that, because I can find infinitesimal movements that I can make along that path, and anywhere along that path that I want to find what was the rotation related to that, I've just got to find my mapping back the way back to my curved space, and that will tell me what rotation that was. Okay, so that's the general idea of what we're going to try and do tonight. Bear in mind that the real thing you need to remember is the problems that we have with rotations. Not trouble that you can multiply them and you get another rotation, but if you add a bit to them, that doesn't work. So in order to try and get that infinitesimal movement, we can't deal in that space. We've got to move to another one. So what we're going to have to find is that mapping. Okay, now we're not going to prove that mapping or anything. We're going to find I'm going to show you the formulas later on that do that. But that's the general idea of everything that we're about to go through here. I'm going to go through the formal mathematics, and I may jump places if I feel that it's not particularly useful. It's always fine when I write down these notes, but when it comes to actually describing them to people, it can be a little bit more difficult. So sometimes I'll just jump when it comes to that. Again, I've mentioned the same 3 acknowledgements from the last one. A lot of this comes from Daniel Kramer's, which again he was using that invitation to 3D vision. So if you'd like to see this in a bit more detail, you can watch his videos and go through that. I'm going to be kind of going through it at a fair old clip. Okay. So the first thing that we need to introduce is the idea of a skew-symmetric matrix, and this is a matrix whereby, so this is a square matrix first of all. And its transpose is equal to the matrix multiplied by -1. Okay, so basically change all the signs. Okay, so in order for this to work, we have to have our diagonal as being all zeros, because obviously the diagonal doesn't move during a transpose, and therefore it couldn't possibly be the negative of the pre-transposed values. Okay, so our diagonal of our square matrix must be all zeros, and then what happens is that the values in the other positions are the negatives of each other. So for example here, if I do a 3 by 3, do a 0 0 0, if I say that this is a value of 1, this position here has to be a -1, and if I say that this is a value of 2, that value there has to be -2, and if I say this is a value of -3, then that value there has to be 3. Okay, so you can see that if you transpose that, you end up with the negative of the thing, of the original matrix. Okay, which is basically if I multiply this matrix by -1, I would get the exact same thing. Okay, many people have come across this idea of a skew-symmetric matrix or anti-symmetric. Have you heard the term before? I don't know whether you would have covered it last year. No? Okay. Okay, well, the good news is you're going to hear nothing but them now for a while, because they're a vitally important thing that we will use. Let's there's a few little things that I've written down here, but actually, if I was going again, I'd probably have written down some different things as well. So all the eigenvalues of A are either 0 or purely imaginary. Now, can you see the trace of this matrix? What would the trace of this matrix be? And remember, the trace is just add the numbers down the diagonal. What will you get? You'll get 0. And if you remember, I said that you could tell something about the eigenvalues of a matrix purely from the trace. It was the same as the eigenvalues all added together. So basically, this is saying that if I add all the eigenvalues together, I'll also get 0. Okay. Now that could happen technically if my eigenvalues were the opposite signs to each other, but that's not the case in this particular case. If we get the eigenvalues of this, they'll all be 0. So what else could you say about this matrix? Is it invertible, do you think? Could we invert this matrix? Okay, so Vin has said no, and you're correct. And the reason is, if all your eigenvalues are 0, your determinant is also 0. In fact, if even one of your eigenvalues is 0, your determinant is 0. And at that point, you've got a singular matrix, and you can't invert it. Okay. So skew-symmetric matrices don't have full rank. Again, is that a term you've heard before? The rank of a matrix? Have you heard that term before? Yes and no's. Okay, so a lot of no's there on that. Okay, so the rank of a matrix. Okay, I mean, I'm not going to go into great detail on it. I'll maybe see if I can get you a YouTube video discussing on it. But basically, if I have a 3 by 3 matrix, if I have full rank, I have a rank of 3, and it basically means that all of my column vectors in it are all linearly independent, which means that they're not no one column is a multiple of the others. So if you do your Gaussian elimination on a matrix and you end up with a full row of zeros, or in some other way end up with a full column of zeros, you've got a rank deficient matrix in some way. These matrices will always have a rank that is even. Okay, so a skew-symmetric matrix will have a rank that is even. So it'll either have 0 as a rank, which means that it has absolutely no, it's basically just a 0 matrix. That's the only way of doing that. It will have a, you could have a rank of 2 for a 3 by 3 matrix, okay? Or you could, you know, if it was a 4 or a 5 or whatever, you could have a rank of 2, you could have a rank of 4, you could have a rank of 6, but you can't have you can't have an uneven rank with these things. Okay, so there's a few things like that about these matrices, but they're particularly useful for some of the things that we're going to do. We're going to use them to model something else, so that's why we mention them here. That second thing there, I don't think it's vitally important for what I want to tell you tonight, so I'm gonna jump it. Okay, so in computer vision, a common skew-symmetric matrix is given by, and this operator. That's not just a little artifact. That's the actual operation. Okay, and I've it down there for a reason. It's normally down in the subscript. Okay, so the cross, we'll call it the cross operation for the moment. Of a vector u in R3. So what I'm dealing with here is I'm dealing with a vector in R3, which we would give as u1, u2, and u3. Okay, and what I can do is I can change that into a 3 by 3 skew-symmetric matrix, whereby I put the u1 there, I put the u2 here, and I put the u3 here, and I put the negatives of these in their positions, u1, u2, and u3, as you can see there. Okay, and I've set this up as a skew-symmetric matrix. So basically that means that if I get the transpose of this, I end up with the negative of it. Okay. And remember that operation, that idea there, it's going to pop up again because we're going to find that something else just happens to be a skew-symmetric matrix, and that turns out to be useful. Okay. So this is a linear operator, and it's not just, we don't just do this for the crack. It turns out that it's quite useful. What it allows us to do is to do the operation of the cross product, the vector cross product. So you've done the dot product of vectors. Have you come across this cross product idea? Have you heard that term? You have. Well, it's a bit of a nuisance then. I left a you can see that that's in blue there, so you can actually click on that link. It'll bring you through to Wikipedia, but it turns out that's one of the things that you do know. So anyways, that'll happen. So if I get the cross product of two vectors, it will give me a result that tells me something, usually about the area that's between them, about the angle that's between them, and so on. So it'll give me some information like that. In particular, what this allows us to do here is that we can, if we do this operation here, so if I take a vector, let's say u here, and I change it to this skew-symmetric form, if I then came along and put my v vector here like that, okay, and said v1, v2, and v3, what I would get when I would multiply this matrix by this vector is I would get the cross product between this vector here and this vector here. Okay? So it has that effect. It'll do that. It'll do the cross product. Now, as it so happens, if I was to put, instead of v here, let's say I wanted to get the cross product of a vector with itself, and I said u1, u2, and u3 there, I would get the cross product with itself, and that would be equal to 0. So, okay, so the cross product of a vector with itself gives me 0, okay? And that's what I've stated down here. Okay, and that is very important. So for the next probably 8 or 9 lectures, you're going to see us use that fact in order to deal with situations. Okay, so what, this is all well and good, but what is the point of it all? Okay, so the cross product is not a straightforward linear algebra operation. So you can't just take one vector and do a cross product with the other as part of your normal linear algebra manipulation. But if you can put it into this skew-symmetric form, then you can. So if you change it from u here, the u vector, to u cross here, then you can actually use that as a standard linear algebra matrix, and it allows you to operate inside of your linear algebra manipulation. Okay, so so the cross product is not, as I say, is not a straightforward linear algebra operation, but it can be encoded as one by changing it to a skew-symmetric matrix, and so can be replaced in linear algebra operations, allowing us to do all the standard manipulation for formula that we do. In turn, every skew-symmetric matrix A, which is following this particular rule, if the matrix follows that, it's a skew-symmetric matrix. That can be identified with some vector, which is just a three-dimensional vector in the space of SO3. Of all the 3x3 skew-symmetric matrices. Okay, so there's two important things here. Firstly, later on in a lot of the manipulation that we do, I will have a vector in there that's a bit of a problem, and I'll want to get rid of it out of some equation. How do I do that? I will multiply both sides by the cross of that u, by the skew-symmetric matrix of that type. I'll multiply across by that. That will zero out one of them on one side. It'll give me something on the other side, but that's usually something that I can deal with. Okay, so when it comes to removing a vector, what's the inverse of a vector? Well, it's this thing. Okay. The second thing is that if you recall, we had the rotation matrices, and we said that there were 3 degrees of freedom. And these 3 degrees of freedom, these 3 pieces of information, can be encoded in a vector, and if we put it in the skew-symmetric form, we still can see just those 3 degrees of freedom. You can see them there. They're just 1, 2, and 3. And of course, these ones are just related to those. Okay. So this allows me to actually deal with that situation whereby I just find those 3 pieces of information, and they're the 3 pieces of information that allow me to do my rotations. So this is going to be very useful for that as well. And this is the idea where the rotations are called a Lie group. So you've come across that term group. You probably never want to come across it again after the last lecture, but that's fine. All I'm telling you there is that this is a group, and therefore the group tells you that as it happens, multiplication works in it. Okay, so that's fine. The lowercase SO3 is its Lie algebra, which is basically this thing that we want to move up into. So if you remember me saying at the beginning that I want to find a mapping from one thing to the other, if I can get it up into this thing here, it allows me to operate in a different place. It allows me to do optimization to find the 3 pieces of information that I'm looking for, and then I can map back to those things. So we have these things, Lie group and Lie algebra. And as you know, algebra, such as linear algebra that you've been doing, we can operate that as part of our linear algebra, different operations that we do. But just because it's a group down here does not mean we can do linear algebra on it. And therefore we need to be able to move between the two. So one is called a Lie group and the other is called a Lie algebra. And again, those terms, like, you've used the term algebra all the time, I'm sure. But when you hear something called an algebra, now you're kind of, oh, wait, what's that? And again, it's just that it has these formal attributes that we allow it to do these things, such as use addition and so on it. Okay, whereas the group, that's not allowed. Now, so we mentioned rigid body motion, and I've said to you up until now that if I do a rigid body motion, well, actually, maybe you can tell me again, what do I preserve here in terms of a rigid body motion? What sort of things get preserved? Yeah, so lengths and angles get preserved, yeah. And straight lines as well, absolutely, yep. So all those things get preserved. There's one other thing gets preserved, by the way. Can you remember what it was? It's the fact that all those things get preserved would mean this other one gets preserved. Yeah, volume actually will get preserved, and we'll have the mathematical formality for that as well. Yeah. Shape, sure. Parallelism was the one I was looking for. Yeah, parallelism. But all those other ones are actually are all preserved as well. But they're all preserved as as a feature of the fact. It's the same with parallelism; it would be preserved because the angles are preserved. Okay, so we have rigid body motions, which are a translation here, or a transformation in R3, plus a translation of some sort of a vector here. Okay, so this preserves the norm, which is, you can think of as just the length, and it preserves the cross product of the two vectors. Now we just mentioned the cross product, and we said that it has something to do with angle. So if it preserves the cross product, what that tells you is that if I've got two vectors, they've got some cross product associated with them. If I do a rigid body motion, they both move in the same way, so we end up with the same cross product at the end of the day. So since the norm and scalar product is just another word for the dot product. So the norm and the scalar product are related by a thing called the polarization identity, which don't need to worry about it too much other than that. But because of that, if we said we preserved the norm and the cross product, then we've also preserved the scalar product. So you can also state that the rigid body motion is a map which preserves inner product, again another term for scalar product, and the cross product. So trying to use all the different terms here as I can. And what that allows us to do, I'm assuming this is one you probably haven't come across. Have you come across this triple product? Have you heard that mentioned? Okay, so basically what this is, I'm going to do my best to kind of draw. Let's say we've a vector in one direction and a vector in another direction. Okay, and the cross product will give you some idea about the lengths of these, but also the cross product will be orthogonal to these. That's why the cross product of a vector with itself is always going to be 0, because it's always orthogonal to it. When we do that, right, if we have some other vector here that is in another direction, let's say it's there, going like that direction there, then what this does is it maps onto that, and it actually tells you, this tells you something about the area, and this other one tells you something about the volume. So when you multiply those two together, we end up with a number, but that number is actually related to the volume. Okay, don't heed my diagram too much, that's not vitally important, but just to be aware that the triple product is related to the volume, which is basically that what we get is we get the cross product between two of the vectors, and then the dot product of that with the third vector. Now, because that's preserved, the triple product is preserved, which is the mathematical identity, we can also say that in the application where we're dealing with volume, the volume is preserved, which again, rigid body, I move this about, the volume can't change. Okay, so since it preserves lengths and orientation, the motion of a rigid body is sufficiently defined by specifying the motion of a Cartesian coordinate frame attached to the object, given by the origin and the orthonormal oriented vectors. Now that's just a complex way of saying, instead of me moving this about, if I just move the world around it and I move further over here, okay, its position compared to everything also moves. Now if that seems a little crazy, all we're dealing with when I say move the world around it, I basically mean that we have a coordinate frame with an origin somewhere, and if I move that origin and I also orient the x, y and z in some other directions, which we call E1, E2 and E3, then if I do that, that's the same as doing this rigid body motion on the actual object itself. The whole point here is that if we move the origin, nothing has happened to the body at all, apart from the fact that it's just further away from the origin and in a different direction, and therefore that's also stating the same thing again. So the motion of the origin can be represented by a translation t in R3, whereas the transformation of the vectors ei is given by new vectors which are basically rotated around. Okay. And that again, that turns out to be useful later on. That what we're basically saying is that any rotation, rather than rotating around x, y and z, what we can do is we can just move a vector to another position whereby we just rotate around one axis. As long as that axis is some combination of the three, there will always be an axis around which we can rotate that will show us the three rotations together. So I don't know, is this vitally important? We'll just mention here. So the scalar and cross product of these vectors are preserved. Again, just mathematically stating that. So there's two constraints that we have up above here, which is this one here, going all the way to there, and then this one here. And the first constraint amounts to the statement, so again, the intuition that the three rotations, R1, R2, and R3 is an orthogonal rotation matrix, which obeys all these rules, as we said. Whereas the second property implies that the determinant of R is a +1. Okay, so that's what those two tell us. R is an element of that group that I mentioned, the special orthogonal group that I mentioned earlier, which, as we said, it's orthogonal, but the ordinary orthogonal group could have a determinant of -1 as well, whereas the special orthogonal group can only have a determinant of +1. And of course, if we do a transpose on it, we end up with the inverse. So if we multiply it by its own transpose, we end up with the identity matrix. So thus, rigid body motion can be written as the following: do a rotation, do a translation, and those two things will do the job. Now, if you're thinking, I've thrown a load of maths at you, but I haven't said anything new, that's absolutely true. I've given you this intuition already, but this is really the mathematical formalism that proves that. And how deep you want to go into that really depends on you yourself. But it also means that later on, if there's something that you're unsure about, you can always come back and go, oh yeah, that's why. Because with most matrices, if I took an A transpose A, I'm not going to end up with the identity. Okay, But if it happens to be that these are rotation matrices which are orthonormal, and I do that, I will end up with the identity. And it's those sort of things that we need to be just that bit sure of to remember. And some of these are just really the mathematical scaffolding that goes around that. Okay. So what we're now going to do is we're going to derive a representation of the infinitesimal rotation, and we're going to do this by considering a family of rotation matrices, or T. Now the T is how much you're rotating by. Okay, so there's how much you're rotating by, the angle, and there's the direction or whatever that you're going to rotate in. And we want this family to continuously transform a point from its origin location to some new location. And we give that by the rotation at position, at angle T, multiplied by our origin vector, gives us our new vector, where that vector has been moved to. And we assume that it's part of that special orthogonal group. Okay, so this is where I said that, the literature will often write something like that on the end of something. You're going to say, well, what's that talking about? It's just, again, that mathematical formalism. Now, we know that the rotation, no matter where it is in that rotation, so I've got some rotation and it's rotating to some final point in some way, okay? No matter where it is in that rotation, if I multiply that by its own transpose, I get the identity. So no matter what my rotation is, no matter what my change in T is, what value T is, it doesn't matter. T is a variable, but it doesn't matter what it changes to. This will always be true. So because of that, this entire your rotation by its transpose, okay, that is constant with respect to whatever angle of rotation that we have. And what that means is that I can say that the derivative of that will always be equal to 0. Okay, because a derivative of a constant, and this is always constant, will always be 0. Okay, so that's the first thing. And again, just look at these things rather than looking at it as a wall of maths. Look at it as a stair step of maths, and you can understand each bit along the way, and then it's a matter of trying to get the whole. All right, would you have any idea how to get the derivative of this, though? That's then the question. So how you do this is basically, I'm sure you remember from maths doing v du dx plus u dv dx. Do you remember doing that? I'm sure you've seen that before, or some version of it. Yeah, so you've seen that before. So basically what we're doing here is we're getting our du dx here, okay? And this is our v, and then we've got our v, and this is our du, or maybe the other way around, whichever way it is, okay? It doesn't really matter, okay? So that's all we have there. It's no big deal. And we know that that's equal to 0. So because of that, I can then move this over to the other side of the equals, where it's just a minus. So I can say that, now that dot, by the way, in case you're not familiar with it, that little dot over that just means the derivative of it. So the derivative of that rotation matrix. It's a shorthand way of doing it. So what we're saying is that the transpose of the rotation matrix by its derivative is equal to the minus of the rotation matrix by the derivative of the transpose. Okay, and this one over here, we can do a little bit of playing about with it. I can get the transpose of it, and to do that I have to change around what's on the inside here. So I'm sure you've done that before. You've changed those around. You swap them around and get the transpose of each. And what that basically leads to, and again, you can take some time at some other stage to look at this, is we end up with this result here, which is that the derivative of 4 multiplied by or transpose is equal to minus the derivative of 4 or transpose all transposed. And if you think about what that actually says, that is basically just saying that if those two are equal, then this thing here must be one of our good friends, a skew-symmetric matrix. Okay? Now, if you're thinking, well, that's great, but I could never have done that. Remember now that whoever came up with this for the first time there was hundreds of years beforehand that nobody had come up with this, okay? And secondly, they didn't probably just pop into their head on that morning. They probably tried loads of different things and then suddenly found, oh wait, this works, okay? So this is an interesting result because it means that the rotation matrix, and remember, or transpose makes no odds. They're the same. They're just the opposites of each other, right? So the that multiplied by the derivative of it, in other words, the small change in the rotation, it turns out that that is a skew-symmetric matrix. And we know that if we've got a skew-symmetric matrix and it's a rotation matrix, so it's a 3 by 3, we can turn that into just 3 values in a vector. So I've just written that with the t put into it now, but it's basically the same thing. We can write that instead as a vector called w, which is just got its cross put on it, and the t is the amount that it's rotated by. Okay. And because we know that, what I can do is I can move this guy over to the other side of the equals, and I end up with that the small minute change, or the small change to the rotation matrix is given by the rotation matrix multiplied by this skew-symmetric matrix that we have. Okay. And the way this works is that if I'm at the identity, if I'm at point 0, I have a rotation matrix that doesn't move. In other words, if I say move by an angle 0, I don't move at all. And if I have, we can see then that therefore for that reason that would be the same as having a skew-symmetric matrix at that time 0, and that is basically the thing that we're looking for. It's that mapping again that I was saying. Okay, it's getting up to there. Okay, so this gives us a first order approximation of the rotation. So going back to this mapping, what we're basically saying here is that if I know my position and I've got a tangent to that, which remember that's what a derivative is a tangent to the space, then I can figure out what it is that I basically have a straight line here. So you can see my pen here is a straight line. Okay, so that's a linear space. So this all kind of works towards what we want to do. And you may remember from a previous lecture that I showed you a thing called a linear approximation. And we said that the linear approximation was what's your position at time 0 and what's your small change that you're making. Okay, well, our position at time 0 is our identity matrix, and the change is given by that skew-symmetric matrix. So what we're saying is we've now got an approximation to our curved space by doing this. Okay. All the time, even if you're not following some of the maths here, don't worry too much about that. The main thing you need to remember is we've got a problem with rotation matrices. We need to find this other mapping to another space, which allows us to do all our playing about that we want to do. Okay. So the above calculations showed that the effect of an infinitesimal rotation on R3 can be approximated by an element from the space of skew-symmetric matrices. And the rotation matrix, or the rotation group SO3, which is called a Lie group, and the space SO3, which is a Lie algebra, and the definition is that a Lie group, or an infinitesimal group, is a smooth manifold, which I kind of showed you here as best I could. It's a smooth manifold that is also a group, such that the group operations multiplication and inversion are smooth maps. Notice that I didn't say addition there. Addition won't be smooth, but if I move it up into this Lie algebra, we can do that. I'm going to jump this because I don't think it's vitally important. We'll come back to it if we ever need to. It's just referring to the distances between things, and there's a particularly useful thing that we can do. But other than that, we'll not mention it. So given the infinitesimal formulation of rotation in terms of the skew-symmetric matrix W cross, is it possible to determine a useful representation of the rotation RT? So now I've got a skew-symmetric matrix. Okay, well, that's well and good, but where is that? Where is that on this rotation map? So how do I get back to that? Okay, so let's assume that Wx is constant in time. Then we have a differential equation here, which is that the rotation at any given time t is given by the skew-symmetric matrix multiplied by the rotation at the time t. And then the other one, that the rotation at 0 is equal to the identity. Okay. We're not going to solve a differential equation here, but I assume you've done some of that in maths in the past. You've done some differential equations and solutions to them. Probably long gone out of your memory now, but hopefully you've covered them. Yeah. Okay. I assume, Niall, you did it in mechanical and places like that as well. Okay, so we're not going to do it here, but just to be aware that what we try to do is we try to find solutions to these yeah, t is an angle. Oh, you're wondering, is it in degrees or radians or something that, or what's your question? Oh, it's not time. Did I say time? Sorry, I meant if I said time, it's just because I'm so used to saying t is time. It is wherever that angle is. Now, of course, if the angle changes with time, it kind of is, and I think that's why we sometimes use this t value here. But yeah, sorry for any confusion there if I said, yeah, it is an angle here. Yeah, okay. But you can think of it as like any variable. Okay, the solution to this differential equation is the exponential function, as it happens. Okay, and what that's basically saying is that if you've got your skew-symmetric matrix at a particular angle t, what you can do is you can get the exponential of that, and that will give you the appropriate rotation matrix. So all you've got to do is you've got to get the exponential of a skew-symmetric matrix, which is a 3 by 3 matrix, and that will get you back down from this nice linear space down to the rotation space, so that you can determine what rotation you actually had. Now, the thing with this is that you're probably aware that in order to calculate an exponential of any number, there's a particular series that you can do. Well, it's the same with matrices. You can do a series. You can start with the identity and then add on these different parts here in order to figure it out. But the trouble is that goes on forever. So in 2 slides time, I'll show you another way of doing that, and it's called Rodrigues equation. But for the moment, that's how we would do that exponential map. So remember, just back to the intuition that I said at the beginning, we can do all our solving up in this tangential space here, which is where our skew-symmetric matrices are. When we solve, where we want to be, we can do a mapping back to that, and to do that we do an exponential. Okay, and we have a particular thing here. What if I want to go the other way? What if I've got a rotation matrix and I want to find out where am I in this map up here? I want to find what is the skew-symmetric matrix that maps to that rotation. So what's the opposite of an exponential? Yep, now we've got 2 answers there. One is just log and the other is ln, and you'll find actually that if you ever see log written without a number down here, you can assume normally that is ln. Now, it is a little bit iffy because sometimes people will just say log and they mean log to the base 10 because we deal in a decimal system, but the natural log is the base one really, and everything else is just human-made number systems. So it is the natural log is the opposite one of the exponential is correct, yeah, okay. But it's fine to say log there, and you'll find particularly in machine learning literature, when they mention the log, they mean the natural log. They definitely don't mean log to the base 10. So this will give us a rotation. When we do this exponential, we'll come to the log one in a second. When we do this rotation, what this effectively means is that this is an angle t, and this is a particular direction vector, okay, and that vector, remember, is given by the details of the 3 pieces of information we have. And what that's basically saying is that any three-dimensional rotation can be done by moving to this vector, okay, the w vector, and rotating by some t around that, and that will deal with all of your other ones as well, okay. So this is the logarithmic map for going in one direction. So as is the case in real analysis, one can define an inverse function to the exponential map by the logarithm. In the context of Lie groups, this will lead to a mapping from a Lie group to a Lie algebra. For any rotation matrix or in this e to the wx, such an element is denoted as wx equals the log of the rotation matrix. And we can deal with the log of the rotation matrix as follows. Basically what we do is we get the trace of the rotation matrix, we subtract 1 from it, we divide it by 2, and then we get the inverse cosine of that, and that will give us our angle. Okay, again, I don't prove this, not entirely certain how to prove it. Our vector then w is given by the three pieces of these different pieces of information within our rotation matrix. So those different or values, we subtract them. As you can see, that's going to land us with a you can think of it as u1, u2, and u3. It's going to land us with three pieces of information to our vector, and we multiply those by 1 over 2 sine of that t value which we've already calculated. Okay, so that's important, and that plays a part in it as well, okay, in order to actually calculate that. So that's the mapping in one direction that we're going to do. Do be aware that, of course, if t goes around 2 pi, we're going to get we're going to get the same thing again. So it's not exactly a non-ambiguous result, but we'll assume in most cases that if a camera rotation has rotated several times, we only need to know the smallest one for that rotation. We don't definitely know that it didn't rotate 3 times between our 2 points. Okay, so that's the logarithmic version. The exponential version then is working back the way. So I showed you previously that we had this series that we could do, but as you're aware, this is something that you remember even from any of you that done the Leaving Cert in Ireland will remember that Euler's equation was in, depending on what age you are, I think it was on page 9 of the log tables, and I know they changed the log tables shortly after I left, I say shortly because I don't want to feel old. I don't know how long it was after I left left secondary school, but there was an equation there for doing that, and you can actually do the same here with this. It's analogous to this, and it's called Rodrigues Formula, and it works as follows. If we know the information such as the t value and the wx, we can work in the other direction, and we can find this here, and this will work out to be the our rotation matrix, or t. Okay, so that will do our job for us there. It's the exponential in the other direction. Okay, so there are the two formulas, and remember back to the main thing that we said tonight, which is that rotations are a problem. We can't optimize them. We can't do a smooth transition between different rotations. So to do that, we have to do all of this stuff. The maths behind it, that's all fine well, as long as you know that you can see that there's two formulas here for jumping between the two, and you have some sense of what they're doing. That's the main thing that I want to get out of tonight. The rest of it is all the mathematical structure that fits around that, so that it doesn't look like I've just pulled this out of a hat, that it is there is mathematical formalism to it, but all of these things kind of have to fit together in order for us to be able to do these things. Okay, so I think we've gone a bit over the time. Apologies for that, and well done for keeping the attention tonight. There was a lot of maths in it tonight, and a lot of new concepts in the maths that you've nothing to grip onto. So if you did find that difficult, don't worry too much about it. There's the main points that I really want you to get out of it, and that's what's important for tonight. Okay, so we'll end the recording there at that.